Hi all, good morning. We're probably gonna wait 5 more minutes to give everyone a little bit more time to arrive, and we should be starting around 8:05, 8:07. Thanks.
Okay, welcome everyone. So today we'll be giving you a true end-to-end of what the forecasting scene looks like in the industry. So yeah, let's get right into who we are, the agenda, and into the notebooks. Can you hear me all right? So I am Ian. I work at Trial Labs, which is a small AI consultancy firm in Uruguay. I've been doing machine learning for 4 years now. And yeah, lots of my experience has been around forecasting. This is Mathieu. He's been working at Google for 7 years as a research scientist mainly, working mostly on temporal data. And around the back is Diego. He's also from Trial Labs, from Uruguay. Has been with us for 3 years and is a director of some sorts at this point, but lots of experience in the technical side. So the tutorial will be divided into 4 notebooks. Yeah.
Your volume is medium, but I don't think your mic is on.
Is it better there? Yeah? Thank you. So 4 notebooks. Part 1 will be a short introduction of the theory behind forecasting, why it matters, what different kinds of forecasting there is, and some more stuff. Notebook 2 will dive into forecasting with statistical or classical methods. That will be around an hour. Then we'll take a quick break. Have in mind this is a very long tutorial course, so we'll have some breaks in between. Notebook 3 will be about forecasting with off-the-shelf tabular models. And notebook 4 will be a bit of the more recent deep learning and foundational models applied to forecasting. All right. Then what we thought would be best for this 4-hour tutorial would be to give you the most time to play with the code and execute the code and try to solve the exercises yourselves. So we will do just a bit of an introduction to each notebook, and then each notebook is quite self-contained, has a lot of theory written in there. So the idea is to give a quick intro for you guys to go through the notebook. Then at the halfway point of the notebook, we'll do a checking. We will resolve some of the exercises or go over some of the most interesting concepts in that notebook together, and then you will continue with the notebook yourselves. All right? That's about it. Anything else for the intro that I'm missing? No? Any questions so far? Great. While you resolve the exercises, the idea is that you can just put up your hand, ask for our help. If it's an interesting question, we might decide to answer it for everyone. If not, we can help you right there. All right? Yeah. So to access these slides, which have the links to the notebooks in this slide, you can do so through the Slack channel if you're on the Slack workspace, and if not, they are linked on the conference site in our slot, right? Does everybody have access to the slides? Great. And I think you'll need to make a copy of the notebook to be able to execute it. So you go to File, save a copy in Drive, and then you can execute it. All right? Great. So first notebook, this is just a short one, an introduction to what forecasting is. Again, lots of content inside it that you will be able to read through in just a minute. Basically, it goes through the reasoning or the need for forecasting, so some use cases on why forecasting is essential for many businesses. That is this right here. Then how to forecast gives a very brief overview of different methods or different ways that one can produce forecasts for a given problem. Then a quick intro on temporal data, which we all know time series is a very normal format to have temporal data in, but there are many other ways in which temporal data can exist and in which machine learning systems can consume this kind of data, such as it not being uniformly sampled, or it being multivariate, or it being some other options. Then goes into forecasting, what a forecast is, what kinds of forecasts one could have. So for example, you could have a forecast for the next item in a time series. You could have one for the next several items or multi-steps in the series. You could have other kinds of statistics you may want to forecast on the series, such as the mean or the max for that next value or those next values, or whether that next value meets a condition or not. So you don't only have the point forecast, but some other options you may find interesting. And that's about it. So we'll give maybe 10 minutes or so. When you finish going through it, there's some questions that you can think the answer to before reading the solution. So maybe when you finish this first notebook, just put a hand up so we can see how everyone's doing, and we'll continue. Okay? Can you raise your hand if you're done reading? Got some? All right. We need to keep going. We try to put a lot of content into this, so the pace might be a little bit optimistic, let's say. But yeah, the notebooks are super self-contained, so if you want to take them home and continue in your own time, that would be great, and the idea is for you to be possible to do that. So a couple of things to comment on this first one. We've got three questions. So, is the data attached to time t necessarily representative of something that happened at time t? If not, can you find a counterexample? Can anyone find one? All right. So as the solution says, the data might not be available at the time that it happened or that it was produced. Sometimes you have lag. So in this case, I think it's an extreme case of data being available, I think 20 minutes later than it was produced, since it has to come from Mars to the Earth. But even in production systems, if you're working with a lot of data, you might have a delay between some logs being produced, let's say, and you having access to them with a timestamp attached to them. In one future notebook, what we'll be also be doing is to each record or to each event attaching some values of events before it, so of past events. So that's another example of an event having data attached to it that isn't actually that didn't actually happen at that point. Second one, can you use a next step forecast model to compute multi-step forecasts? You can. This is called autoregressive or recursive forecasting. So the idea is you have a model that predicts for the next day. So based on whatever data you have, you predict for, let's say, tomorrow, if it's a daily forecast. Then once you have the forecast for that next day, you can take that as past data and use it to forecast the one for the following day. So in this way, with a single model trying to forecast for a single step, you can do multi-step forecasting. Then I think it's important to mention the concept of horizon, which I think is somewhere here. When we say we are forecasting for several horizons, that just means for several points ahead. So we might be forecasting for horizons 1 through 7 in a weather app, because we want to know the weather for tomorrow, for the next day after tomorrow, and for the next week. So every horizon stands for one of these steps that we are forecasting for. We will be using this concept throughout the notebooks. And then for the last question, can you use a multi-step forecaster to generate aggregated or conditional predictions? The answer is that you can, but as it said in the introduction to aggregated forecasts, it might be easier to just forecast directly the value that you are interested in than trying to forecast the point predictions for several other values, which might be more noisy, rather than just going for the total or the average that you care about and training a single model on that signal that might be much less noisy. So that's all for notebook 1. That was the introduction. Any questions before we go into statistical forecasting? Great. So I think, Diego, you're up.
Fantastic. So that was a little warm up. The idea now is that the three following notebooks are going to be a little bit heavier on the code and on the theory. And the idea is that throughout this tutorial today, we want to walk you through the process of how we traditionally did forecasting in the past, what techniques can we use today, and of course, we're going to be talking about Temporal, which is a library that we developed in collaboration, Trilos and Google, that can help you pre-process temporal features. So before we get started into the fun parts, like dealing with large amounts of data and using deep learning or foundational models, we want to go through the basics to make sure that everyone is on the same page. And the way we're going to do that is go through this notebook part 2, which is all about statistical forecasting. So statistical forecasting are those methods that you might have known from the 60s, 50s, maybe more. So your ARIMAs, your SARIMAs, your exponential smoothings, etc. So the idea on this notebook is that we're going to be dealing with 2 data sets. You're going to be downloading these data sets. You're going to be plotting them. You're going to be asked some questions regarding how to split temporal data, how to create train validation and test data sets. You're going to discuss a little bit about metrics and the way we evaluate forecasting models. And here you will see there's places for you to write your code. So the idea is that as you go and execute, take your time, fill the cells, and at some point throughout the tutorial, we're going to have some checkpoints to make sure that everyone managed to solve it. And if you have any questions, we're going to be able to answer them. The solution is here, is hidden. Please give it a try before you look at the solution and keep on executing. This tutorial makes a lot more sense if you do that. So again, if you at some point you're stuck, the solution is there, but you get a lot more out of today if you take the time to think through these exercises. We're gonna look at some models, again, traditional ones or ARIMA, SARIMA, exponential smoothing. And then at the end of this notebook, we're gonna get into a little bit of something that's more advanced. It's called, we have it here, forecast reconciliation. And this idea is that sometimes we might have hierarchical forecasting, so we might want to forecast sales across stores, and we might be interested in the forecast of individual stores, but of the company as a whole. And if we have individual forecasts, it might be the case that when we add the individual forecasts, it doesn't add up to the total. And so how can we use individual forecasts to improve the aggregated one and vice versa? And so there's also a little bit of exercises at the end regarding that. Having said this, the idea here is that I'm going to give you around 20 minutes so that you can start executing, you can start playing, you can start going through these exercises. At 20 minutes from now, we're going to have a checkpoint. I'm going to show some of the solutions, and I'm going to give you some more time to sort of keep on going through the notebook. So 40 minutes to go through this whole thing, 20 minutes to go sort of halfway. And if you have any questions, please raise your hands, and we're going to be happy to help you. Any questions? Was it clear? Does everyone have access to this notebook and can execute? Awesome. Have fun. You might be running into some NumPy issues here. Basically, there's some issues with versions, and NumPy just released version 2.0, so some libraries are sort of having some trouble with that. If you run this cell, this should fix it, but sometimes you need to restart the runtime. So go to runtime and restart session after you do the pip install, and that should be able to let you execute as planned.
We'll do the halfway checking in about 5 minutes, and it will be up to the STL part, just so you can manage your time. Again, no need to go super in depth on every concept we are presenting. We know this is a fast pace. We are introducing concepts at a higher level, not super in depth. So yeah, in about 5 minutes, you should be around here. And if not, no worries, we'll go over it.
All right. So welcome to check-in number 1. The idea here is that we have some time for you to ask questions, for us to review some of these concepts. Just to get a feeling of the room, how many of you have reached this point in the notebook? How many of you have yet to reach this point but are working towards it? Okay, so we might need to adjust some of our schedules today. No worries. Have you made it to... Let me find a point that is interesting. Well, we can leave you 5 more minutes and then get back to this. Or 10. All right, let's start this first check-in. So, as I was mentioning earlier, the idea behind this check-in, behind this notebook, is getting started with forecasting. And what we're gonna we're gonna be using is this data set about month and number of passengers. So the first thing that we need to be able to do whenever we are dealing with temporal series is plotting. Plotting is really important, especially because we're going to be using metrics, and those metrics sometimes are a bit not representative of what's going on. And so always plotting your time series or time sequences is really important to understand and get some insights on what's going on. So this is what our time series looks like. And the next thing we want to do is we want to use this for machine learning. We need to do train validation and test. As you probably read, this is a bad idea. So what we do is we find a date and we say, okay, everything after this date is going to be test. Everything before this date is going to be train. We often refer to that as leakage, and that's a very common problem in time series. So if you went through the solution, this is very simple. We're working with pandas data frames. And what we're saying here is filter everything so that it's before a given date, or filter everything that is after a given date. And of course, make sure that your equality signs are only on one of these. Otherwise, again, you run into leakage. So we have our train and test. We can split it. As you can see here, we get to see the cutoff point after which we have train and test. We have different colors for this. And the next step is to have evaluation metrics. We are going to be using this across this tutorial today. And so the most traditional ones are the mean square error, the mean absolute error, and the MAPE. Absolute percentage error. And there's some reasons why you might prefer one to the other. I think there's some explanation here. Otherwise, feel free to go and read more about them. But as a one-liner, if you think outliers might be an issue, avoid MSE because that square really punishes you for that. And yeah, so the first exercise was to create a very simple validator, a very simple forecaster that only copies the last forecast. And so this is literally saying, okay, my prediction is going to be the last value. If you plot this, you get something like this straight line, which makes sense because this is the last point we have access information to. And then when we generate the next forecast, that's exactly the last value. And because we have no new information, basically we keep on copying that point into the future. This is, of course, a trivial forecast. We can calculate some metrics for that. And the solution is, okay, how do we start using better models for this? And so we start looking into statistical models. Here we have this combination of autoregressive models that are a linear combination of past features, moving average models that basically look into moving averages, and we can start building combinations of all these things. That's traditionally called ARIMA. Bless you. And what you can see here is that if we start training these models, for example, using egg lags is the term we use to refer to steps looking back. So if my time series has one tick every month, then lags equals 8 means going back 8 months and using that information to predict about the future. In this case, if we're looking about monthly data, you might think that 8 is a quite arbitrary number, because 6 or 12 or 3 might be better. So our model is not very good, and we can see it here. But again, it's very important to plot our model here. Again, it's much better than the previous model, and we can see that evidently from the metrics. All the metrics go down, so that's good. And we can look at the parameters that our model created. So basically, these are the coefficients of this statistical model. And we could try to interpret this if the model was sort of a decent fit. But again, you see that the value that seems to be the most relevant is the most recent one in time, L1. And this makes sense because one would expect that if the time series doesn't change very rapidly, the last value is sort of a good predictor of the next value. So moving on, we keep on trying different models. We get better models by, again, doing this 12 of 24 lag idea, as I was mentioning. This is intuitive because the more data we give the model, the better it should behave, but also there's this notion that if we're looking at monthly data, looking at yearly ranges, so multiples of 12 should make sense. If we want to get, then the notebook gets into what we call more interesting models. And so this is the first time we're going to be using ARIMA. ARIMA is sort of the golden standard of statistical models. And the idea about ARIMA is that we're going to have, we're going to try to mix all these ideas. We're going to try to keep this idea of having a linear combination of my previous values, the lags. I want to have some combination, some of my moving averages, but I also want to make sure that if there's any trend in my data, if my data is increasing, for example, that I can take account of that. And so we have these 3 parameters here that I'm pretty sure you all read about them as you were doing the notebook. And we can fit a model. There's a lot of libraries out of the box that allow you to fit these statistical models. So what we do is we fit our model here using the endogenous data as the number of passengers. Here, endogenous means the data about the time series itself, and it's in opposition to exogenous data that might be, for example, the weather, which is sort of might affect my original time series, and it's information that I might want to take into account, but it's not the time series that I'm forecasting per se. I can forecast several steps ahead, so we can get our forecast here, and then we can plot it and get results. So far, so good. Any questions? Yes?
The P, Q, and D. Can you give me like an intuitive idea of like what those stand for?
The question is, what's a good intuitive idea of what PQD stands for?
The first answer is it's not super intuitive.
Yeah. Like, if it stands for anything, I know that D stands for difference because to remove the trend, what you do is basically you create a new time series that is the original one minus the one step before. Because the idea is that if you're adding something at every step, you're sort of removing that. And so that D stands for how many times you difference that time series. Where the P and the Q comes from, I don't know.
The P and Q are how many terms you're using for the autoregressive part and the moving average part. So the autoregressive part is the one that based on a fixed amount of lagged values, you create a linear combination of those for your prediction. So P is how many lags you're using for that one. Right, because in the previous model we had seen that 12 actually worked well. And Q is the same, but for the moving average part. So the other half that is a bit harder to explain, and we will go into detail today, but it's how many terms you are using for that second part. That is also a linear combination, but of the error terms of past values, let's say. Okay.
Yes?
So in the calculation of MEP, there is a use of epsilon. So can you elaborate under what kind of situation the use of epsilon is necessary?
Yes, your question was when we're calculating the metrics here, there's an epsilon, and the problem here is that your time series might be 0, and then you're dividing by 0, and then you're in trouble. And so this is a workaround around that. Basically, it fixes having to divide by 0. I mean, you don't have that issue in the other ones because you're never dividing by the time series, which might take 0 as a value. Yes. Time series. Yes. And the idea is that often when you're working with time sequences, you do things to go back to the time series to apply your models, unless you're doing some of the things we're going to be seeing in the next notebooks. So yeah, for most of these models in statistical forecasting, we assume that everything is sampled uniformly. So as they were asking here at the front row, when we think about good values for P, Q, and D, indeed, P, which stands for the number of lags that we look back, 12 sounds like a very good value because, again, this is monthly data, and so it makes sense to work with yearly data. And we also see an increasing trend. So we know that for the I part of ARIMA, we want to have some differences because we want to remove the trend. But how do we formalize that idea? The idea that there might be trends and things like that. This is not run. So we had a version of the notebook that was run before, so without the outputs, which is not here. But we're going to do a live demo because those always work exactly as you planned. So if you have your notebooks with you while we do this, you see that we introduce the autocorrelation plot just before this. And the idea behind the autocorrelation plot, it's a little bit strange the first time you look at it, is the one with all the individual spikes. And the idea behind that plot is that knowing, you might have some intuition of what the good values are for your lags, but if you don't know about the problem, that one. If you don't know about your problem, then you might have a hard time finding this. And so what this plot shows is basically the correlation between a given time, a given point in your time series and the same point some time before, some given amount of lags before. And the idea is that if those points are correlated because those are spikes all the time within your model, then the correlation should be high. And if, again, on the contrary, one is a peak and one is a valley, then the correlation should be lower. And so just from looking at this plot, we can see that, okay, the correlation is fairly high for the first lag because, again, if we look just yesterday, then that's probably a good estimator of my current value. But then that continues to go down and all the way until 12 when it actually peaks again. And this is because we have this seasonality in our data. So this plot, it's also like a good tool to analyze your data. Finally, we're gonna close this checking session with this plot. The STL plot allows you to decompose your time series into 3 components. So on the top plot, you get your original time series. On the second plot, you get your trend. On the third plot, you get your season. And on the third one, you get your residuals. And the idea behind this is that it's a very good way to see if your time series has a trend. Is it increasing or decreasing? Yes, very easy to see. Does it have some seasonality patterns to it? Yes, it's very easy to see that it goes and oscillates. And then we get the residuals, which is basically everything that could not be explained by these two factors. So again, good tools to understand your time series and that you can use to manually infer the parameters for a statistical model that you might be plotting afterwards. Having said this, we are going to change a little bit the schedule of today because there's snacks outside, and so I'm pretty sure you want to get some of those. So we're going to do a small break here, 10 minutes, and then we can come back and finish this notebook. So it's 9:15. Let's be back 9:25. So we can start 9:30. All right, welcome back. We're gonna be taking about 10 minutes, 15 minutes to continue working on this notebook. And after that, we're gonna do this small check-in, answer some questions, and start getting into the fun part when we use fun machine learning models for this. There's a part at the end, it's called reconciliation. I think I mentioned it very briefly when I introduced this notebook. That might be the harder part of this. So if you get the general ideas, I think we're good to go.
By the way, we are monitoring the Slack channel, so if you have questions that you'd rather write there for us to answer, that's okay too.
All right. Hope you had fun with that second part of this notebook. The idea is we're going to take 15 minutes to run over some of these cells and sort of have some parting thoughts about this notebook. Also, of course, if you have questions, you can ask them now. If you have questions about this later, the Slack channel, it's a great way to for us to keep on answering them even after this talk. So if you go back home and you actually want to give it a try and you run into some issues, feel free to ask them in the Slack channel. So the idea about this notebook was to introduce you to standard statistical forecasting methods. R, ARIMA, SARIMA, SARIMA X, and the whole family of SARIMA models are probably the most traditional ones, but there is probably one more that is also very well known. It's called exponential smoothing. And the idea is that we are gonna do something similar as we did with ARIMA. We're gonna look at our lags or previous time steps to make a prediction about the future. But this time we're gonna change how much weight we put to each individual value. So the idea is that we have our prediction, and then we're gonna update this prediction based on the last value weighted by parameter alpha and the newest observation. So basically, each new observation is forcing our current model either upwards or downwards based on this factor. This model is very simple, and as it is, it's not as good, but we can make it more complex. We can start adding more things. We can add seasonal patterns. We can add trends. And so in the exercise here, the idea was to try to train one model using these things and see what you get. If this is the first time you're seeing this might not feel very intuitive. These ideas that we can add, when we say errors, what we mean is when we have a time series, we have what we predicted and the actual values that we can observe, especially looking to the past. And so we can actually calculate the difference between our predictions and the real values. And we can look at the time series of errors that we had. And so the question is, that is probably useful information. How do we want to add that to the model? Do we want to add that to the model? Do we want the model to be multiplied by that time series? Same thing for the trend and the seasonality. These are not as easy to understand as we would like. And so we could probably spend 30 minutes doing a deep dive into why you should do seasonal being a multiplicative pattern versus errors being additive. I think that what you should take out of this is that this is a different family of models. These are simpler statistical models that provide decent or good results when you have univariate time series, which is the case here, and can be a very good baseline if you're just starting out with a new model. So here you can see it's actually, it might be the best model that we tried, depending on the metric. And again, here you see, depending on the metric, some models may be better than others. So again, keep this in mind when choosing which metrics to use.
There was a question in the Slack channel about not being able to make ARIMA reach as good results as our last ARMA model. The answer was sometimes a more complex model is harder to fit or harder to optimize. So in this case, actually for our data, the simpler model, ARMA, with the 24 months lags was actually the best one, rather than ARIMA, even though ARIMA is a more capable model.
Yes, and this literally ties very well with the next section here, automated models. The same way we do, yes. Yes, in a way, the idea here is that because the seasonality is growing over time and it's not static, then you should favor a model that is multiplicative so that the new values of the time series, as they're increasing, also affect the seasonality. Yes. This plot definitely might help you. Basically, this is the error plot. So, like, trying to understand how this fits within the whole thing is definitely like a good place to start. As with every machine learning model, we have hyperparameters. And if you don't know where to start, you can always do search. And so there's very good packages to do, for example, AutoTS or AutoARIMA, which basically try a lot of parameters and based on some heuristics try to find what's the best model. And here they try to strike a balance, as Ian was saying, between accuracy of fitting but maybe overfitting and complexity of the models. And so there's a whole family of scores on how good your model is. I would say that this sort of concludes statistical forecasting. These are the less powerful methods, the methods that we have been using for the longest time. I don't know if I would recommend you to start here today. Probably the next two notebooks are a better starting point. But there are things that come with statistical forecasting models that we don't have in traditional machine learning, that are the reasons why these are still here. And that's because we sometimes can get statistical guarantees about our predictions. So for example, we can get things like, I think the predicted value is 34, but I have this confidence interval of this level that the predictions are within this range. And so for many applications, having those statistical guarantees is very important. And you might decide that you want a weaker model because those guarantees are important. If you're just doing forecasting for a random application in real life and you just want to get the faster, the best, most accurate model, this is probably not the place to start. And we're gonna see right ahead how to do that. The last thing. They offer guarantees. The other models don't offer any guarantees. So if you're doing a deep learning on time series, good luck with that value. Like there's no guarantees that that is a good prediction whatsoever. But it's probably, you look at the tested and the accuracy might be half, and you might say, okay, this is still twice as good as the other model, so I'm still gonna trust that this thing is gonna work. The last thing I mentioned here is reconciliation, and this idea is that if you have this structure of hierarchical time series, you might want to use that information somehow. And so here you're working with a different data set. This data set is about trips in Australia, and we have different regions, and so we get this layer structure. Trips for a given purpose in a given region. And so we can aggregate all that. We can look at, this is quarterly data, not monthly data. And so we have for each state, how much trips were done each quarter. And here we're introducing Temporian. Some people were asking, what is Temporian? Temporian is a library for temporal feature extraction and manipulation. And you're gonna get a much better explanation of it in a second. But here we can see that without having to use matplotlib and actually run a for loop, we can very easily preview this time series. And so these are all different time series that we are interested in forecasting. What's relevant here is that we're also interested in the total aggregated number of trips. And so we might have to forecast that separately. There is a simple way of doing that, which is basically, here we use a transform. Basically, the only thing that does is it gives us the total. And we have the total here. This is basically the aggregation. You can see in the y-axis that this is a lot larger than the others. Makes sense? And now we can simply train models. Here we're using the ETS model, and we are looping through each state. And we are training a model for each state. These models are okay-ish. Again, the goal at this point is not just to get the best model, but rather get a prediction for each one of these time series. We're also getting a prediction for the total. So we have a model that's specifically trained on the aggregated of all these states, and we get a prediction for that. We can look at the error. Some of these states don't do very well. We could, of course, start iterating, do some hyperparameter tuning and get better models. But the idea here is to use reconciliation. Yes? Where? Let me see what this is trying to say. The raw plus substance conclusion with dangerous and I think that what this is just trying to say is sometimes because these things oscillate, it might not be as obvious that there's a trend, and so if you're actually trying to understand if there's a trend, there's a tool for that, and that's more reliable than simple eye inspection. Yes, I mean, sometimes it's obvious and you can say there's a trend, but sometimes a couple of peaks hide the fact that on average it's not growing that much, or you might overestimate how much that trend is. And so that's simply a recommendation. If you're interested in the trend, the SEL plot might give you just that information, and it's easier to. And so we have models for each one of these time series. question is, can we do something better? Like we can, of course, we can iterate on each one of these individual models, but can we do something to fix them all without training better models for each? And the idea is that if I know that all these states need to add up to the total, because that's the way it works, then I can use that information to feed it back to the forecast. I can add all my forecasts and see if it matches the total, and if it doesn't, then I know that something is wrong. And what I can do is I can look at the historic of my forecast and see how that relation has been panning out, and I can try to find some heuristics of saying, okay, maybe this state is often half of the total amount of sales. And so if in my forecast it's only 40, I might try to push it a little bit higher. And that might fix my forecast in general. Instead of doing that by hand, which can be cumbersome and very error prone, the idea is that you have methods that do that automatically. And what they do is they fit a model, in this case as ordinary least squares, to find the relationship between all these series, the higher level and the upper level. And then we use those parameters, those things we learned from this optimization problem, to feed it back to our forecast and change them in a way that reduces the error. The way that's done involves a lot of very specific matrix multiplication, some variance minimization that I don't want to get into details right now. But if you have any questions, feel free to ask them. I'm happy to answer them here via Slack. And so we can use this model. This is simply importing from a library called skTime. And we transform our forecast using the reconciler. And that gives us new forecasts. And after a little bit of pandas magic to get all this together, we can see the result of our original models and our reconciled, and we see that in most cases we actually decrease the error, which is great because we didn't have to train a new model, kind of. And so basically the only thing we did is we took our forecast and we say, okay, we know that these forecasts need to add to this forecast, and we know how that panned out in the past. So let's make sure that we use this information to fix them after the fact that we have forecasted. And so these sort of techniques don't come into play often because not always you have these sort of hierarchical time series, but if you do, it could be a very useful thing to just boost your models a little bit. Having said that, this concludes notebook part 2, statistical forecasting, and we're gonna get into the good fun parts. And so I'm gonna leave you with Matthew, which is gonna introduce you to Temporian.
We'll do the first part of this third notebook, then take a little break and come back after, right? So one more break in about half an hour, 40 minutes.
Thank you, Diego. All right. All right, so we are in notebook number 3, the second part. So in the first part, we studied a little bit about statistical forecasting. In this part, we're going to completely change gear, right? So in this category, we're going to study forecasting methods that are based on tabular model. So let me introduce that a little bit. So in the previous part, you studied models that were designed to forecast time series, and this has been work of research for a long time. In the second part, we're going to use the work made by people that do machine learning model on tabular data, so something that has nothing to do with time series, and find a way to adapt it to time series forecasting. The big idea is that there is a lot of work that has been done on tabular data, so being able to pull this knowledge from other domains leads to really, really good results in practice. A point that is important is that it's a completely different family of technique, and you might ask yourself, hey, why are you guys showing this much different technique? What's in it for me? So the big main reason is that there is no one technique that is always better. So in your product, if you really want to have the best forecast, the best thing you can do today is just to try different methods and see the one that works the best for you. Of course, as you do that, you will develop expert knowledge. So if you see a problem, you might have your gut feeling that say, okay, for this problem, those are probably the 2 or 3 techniques that are worth testing. The other one maybe don't matter that much. Another point that is important is that knowing a lot of different techniques is a way for you to build your understanding, your gut feeling about forecasting. And machine learning, applied machine learning is still pretty much an art. So there is a lot about practicing and learning, and this is the great way to do that. Just one note before we go in this tutorial. So there is another tutorial this afternoon given by the author of the SK-Time library that Diego mentioned before. So if you want an even deeper tutorial into this mostly statistical forecasting aspect, make sure to visit this other tutorial. All right, so for this tutorial, the idea is to do forecasting with off-the-shelf tabular model. The big idea here is that we will use a much more complex data set than the air traffic or the Australian data set we had before. This is a data set that looks much more like what you'll have in production. So for example, we'll have a data set with multiple time series, data that is sampled non-uniformly. You might have values that are not just numerical. You might have text, you can have image, you can have categories, you can have those kind of things. So the techniques that we're going to show in this notebook is much more flexible to this type of data. So in the first part of the notebook, you will learn about this data set. We will plot it. You will discover what this data set is about. Then what we'll work on is to define the labels and the feature for this data set. So in standard tabular data machine learning, you always have the concept of features and labels. So this is what we'll define. We'll also place with a train test split. So the same way we did before, but we're going to extend this concept here. And once our data set or label and feature are computed, we're going to actually to train a model. So we're going to train a model, and then we're going to evaluate the model, and we're going to iteratively add more and more feature and see hopefully that the quality of the model increase. And this is pretty much what this notebook is about. So as same as for the next notebook, we'll have a check in the middle of the notebook. We will put the check just before we enter the YDF section. So if you see YDF, you know that this is where we're going to catch up in 20 minutes or so. All right, good luck. Yeah. Of course. You should use both, and they are extremely complementary. So we have a little pitch about temporal when we reach that. SK-Time initially was, the author of the SK-Time will talk much better about SK-Time that I will do, but very informally, SK-Time is a library that contains a lot of statistical forecasting learning methods, and actually they extended. Now it's more of a framework, and they're able to do deep learning and this kind of things. So it's really a machine learning framework for forecasting. Temporal doesn't do any machine learning. Temporal is just about preprocessing the data, the temporal data, before you use likely machine learning, but also something else. So the parallel we give is temporal is kind of the pandas for temporal data. You can use Panda to prepare your data before you use XGBoost or something like that. The same way you can use temporal before you use SK-Time or some other ML framework. Oh yeah, of course. So one of the things that matters a lot is ease of use and making sure people don't make a lot of mistakes when they use those library. So temporal is really a small piece, but that does what it needs to do very well, very fast, and connects very nicely with other framework. And so we'll show how temporal connects with pandas here, but we'll comment also in other type of decoration. Oh yeah, of course. And temporal is integrated in SK-Time. So if you use a SK-Time pipeline system, you can have temporal nodes that do the pre-processing before the other machine learning node. Right. Wait, it's not released on. It's not released on Windows yet. It should come at some point. Sorry if you're a Windows user.
All right, welcome to this check-in. We are gonna be back with you in a second once we know how to hack someone else's laptop.
All right, first check-in. Just by a show of hand, how many people are at this point? I see a lot of people looking up, so I suppose this is good. All right, let me very quickly go over what you've done, give some extra comments, and then you'll attack the second part. All right, so we talked about the M5 dataset, this competition dataset that shows a lot of interesting feature that you might have in real datasets. We load the datasets. We subsample the dataset. A word about dataset subsampling. When you design a model, a machine learning model or a forecasting model, it's really important that you have good velocity during your development. It's important that you try a lot of things, you debug, you look at things. If training a model takes 2 days, you won't have a lot of velocity. You won't be able to iterate. So the good advice is always start with the smallest possible dataset with aggressive subsampling. Be careful with the conclusion you draw from it, because if you have a very small dataset, your training won't be that good. But it's a good way for you to play with things. And if I do the analogy with this tutorial, once you are done with that, you remove the subsampling and you have the full model at the end. So this was a word of subsampling. All right, so then we introduce Temporal. So Temporal is a product, a library that we developed. And for the sake of preprocessing the data from the temporal format into the tabular format that is compatible with our tabular machine learning model. So here we have a little bit of example of what Temporal can do in the symbol setup. Then we want to apply it on our data sets. So if you play with real data, you might have faced with this problem that each piece of your data set is represented differently. So here we typically have an example where your different tables have different time representation. It's always a good idea to align things. All right, a lot of normalization. The calendars. And then we attack the feature engineering. In the grand scheme of things, when you do ML, the sexy thing is always a machine learning model. But in a lot of places, in practice, what matters a lot is your data, your feature. It's not always true, but it's mostly true, I think. So feature engineering is really the important part in ML. We start with the simplest possible machine feature extraction we can have, the lags. We'll look at the solution. All right, we prepare the labels. So you guys all got the idea that a lag is we look in the past, and label we look in the future. And the idea is to predict the future from the past, right? So you have this lag system. On the horizon, so something that you've noted is that we created multiple labels, one for each of the different horizon steps. So one label is next day, so another label is today in the future, and so on. And which means that we have a lot of different type of label. An alternative that we didn't show here, but which was used in the first notebook, was instead of having a single label, which would be next day, and to apply multiple times your model, once to predict the next day, but then to feed back this prediction back into your model to predict the other days. So those are two big differences in modeling choice. So here we demonstrate the non-autoregressive part, and the first notebook was the autoregressive version. And then we do the train and test. Oh yeah, this is really important. So the same as for the first notebook, you've seen that we create a limit and we say everything that is above become more training data, everything that is after is our test data. This is a simple example. In practice, when you want to have good trust in your system, you want to do that multiple times, right? You will use multiple checkpoints, and you will aggregate the result you get on top of that. But doing that introduce some problem. The biggest problem you have is that if you have multiple cut points, the cut point that is the early has actually very little training data and a lot of testing data. Compare if you have a cut point that is near the end of your data set, you have a lot of training data and a very small amount of test data. In addition, if you're modeling a system that is dynamical, a system that changes over time, like most of our system, if you do a train test at the beginning of your data set, it might become irrelevant for your use case. So those are all the actually quite important considerations that we don't cover in this notebook. But here the idea is for you to essentially play with those concepts, and once you grab those concepts, I think those checks come naturally. So in this example, simple possible version, we just have one cutoff. Actually, we have two cutoff. You got the idea that to compute the feature at time t, we need to aggregate data from the past, right? So the basic idea of starting your training data as soon as you have data is not very good, because you don't have historical data on your first test training data point to compute those features. And maybe just a story related to that, because it's something that happened a lot. So here we show some very simple feature processing. Next section show much more. A very common feature preprocessing, especially with neural network, is feature normalization, also called z-score. The basic idea is you look at the entire data and you use it to compute the mean and the variance, and you normalize your data by mean and variance. Works very well. But when you think about it, it's kind of cheating, because the mean and variance has been computed on your entire data, but you use it to normalize each point of your data. So in a way, your first data point is normalized using data from what comes after in your data set. This is an example of feature leakage. You need to think about it, and when you think about it, it's very easy to do those kind of leakage. So this shows the importance of being careful when you do those kind of things. Oh yeah, one thing that is also important in train test is you've noticed that we do the train test after computing the feature, not before. So we compute the feature on all the data set, and then we cut the data set in half. If you do machine learning in general, you might see a lot of examples when this is do the other way around, because generally it's simpler to do the other way around. For temporal data, you cannot do the other way around. The reason is because your first test data rely on features that are computed from data in your train. This is why you need to do your cut after. Again, if you think more about it, it's clear, and this is why it's important to play with the data. All right, so we computed the label, we computed the feature, and we aggregated a train and test data set, and we are ready now to actually train a model and evaluate it. And I'll let you for the next section, and in 20 minutes we'll cover your things. Oh yeah, if you have question, this is the right time. And before you go to the next section, we invite you to take a little bit of a break, so you have a fresh mind for the next. All right, no question. Oh yeah.
Roughly, where would you expect to be after the next time?
So we have 10-minute breaks, and we leave 20 minutes more to finish this notebook. Yeah. And then we'll have another notebook, right?
We are a bit short on time, so yeah, break, and we'll be back 5 to 11. Okay? Yeah, second half of this notebook we will finish after the break. Okay, so you should continue with the second half of this notebook. 20 past will do the wrap up for this one and do the last notebook after that, and that's about it.
All right. So I assume everybody has not yet finished the notebook, but we really need to go over it because there is another really, really important notebook after. So let me try to go over the things you've done, to comment, and hopefully to give some good insights. All right, so what you've done is you train a decision forest model, a tabular model, on top of your tabular data. And then you've, it's not run. You've displayed the model. One point here. So at the beginning of the notebook, we say it's really important for you to look at your data, to plot. This is always the first things to do. The same apply here. Once you have a model, it's really important for you to plot the model, to look at what this model. So when you run the model describe, you should have a little box with different tabs, and this is a good way for you to look at what's inside of the model and have a clue over it. All right, we train the model, and then you see there is quite a lot of code when we shuffle the different data representation. So our data is stored in temporal and event sets. The model returns NumPy array. Luckily for us, the Python ecosystem is really good to essentially convert those different data formats. I find it really useful to try to always convert everything into a single format. In this case, we choose temporal. It'll just make your life easy in development in production. All right, so we evaluate the model, we compute the prediction, we plot the prediction. So again, always looking at your data. Your prediction is also a type of data. And that's it. So at this point, we've been able to define feature, train a model, evaluate the model. So we have an end-to-end pipeline. It's a very bad one because we have almost no feature. Those are just lax feature. But we have our end-to-end pipeline. So what here is, it's a really good idea to start to do that. Do your end pipeline end-to-end, where each of your components, cleaning, feature engineering, modeling, is as small as possible. And then in the next stage, you polish it. The opposite is to develop each component to the full extent before you combine them. In practice, this doesn't work. So always try to do your all full end-to-end pipeline and then refine it. And this is what we're going to do after. A word on feature. So as I mentioned, the feature engineering is a really, really important part for this kind of modeling. One reason this is important is because it's a nice way for you to inject your expert knowledge. When you model a system, you have a lot of insight about what works in the system, what matters, and what's not. The feature engineering is really a good way for you to input that. The corollary to that, one trick that we see a lot is you can have someone that say, hey, look, I've got this data available, but this data is really not useful for that model, so I'm not going to give it to this model. This is not a good idea. Models are really, really good to aggregate a lot of data, to merge all those clues together. So the right approach here is feed all the data you can to your model, and then ask the model what feature matter or not. Like the model is able to tell you, hey, this feature is really useless to me. So let the model do that. And you'll be surprised how many feature models are able to consume. All right, so here we create more feature. So we've got moving statistics feature, calendar feature. When you model human activity, you should always have calendar feature. Human activity are extremely dependent on the time of the day of the week, all those kind of things. So always have them. Moving statistics, calendar feature, calendar events. Here we show also a hierarchical aggregation. So in the previous notebook, we show how to handle hierarchical data using reconciliation. Here's just another way to handle hierarchical data. This is to show that there is a lot of different techniques that can apply, and it becomes part of your expertise to try them out and figure what works well for you. So we train, hopefully the model quality improve as we add more feature. This is kind of this iterative process that we talked about. And you have your evaluation. One word of evaluation, so here we use the RMSE, which is kind of the default metric that is used in academics. It's a very simple metric to compute. It's extremely stable. So that's why we use here. But in practice, this is not a good metric for your use case. when you use a model in production, a forecaster like that, what you need to optimize is your business metric. Generally, it's something in dollars. So it's really your job as a developer to figure how do I make my model optimize my business objective. It's not always easy, but you'll have to learn to figure that out. And it's not always possible. So for example, maybe the model is not able to optimize a very complex business metrics. So your goal will be to create alternatives that are close enough to your business metrics for your model to optimize. One thing though, it's really hard to optimize complex evaluation metrics, to learn model on complex metrics, but it's generally much simpler to evaluate them. So your evaluation component in your pipeline should be able to evaluate your business metric or something as close as possible. And in real production pipeline, you might have your evaluation component being something very, very complex that might include simulation and things like that. It's completely okay. And then you use your whole pipeline to make your decision on your feature and all of that. All right, so this is the end of this part 3. And I'm going to leave the mic to Jan for the next section that he's going to talk to you about deep learning forecasting.
Great. So I would say that what was shown in this last notebook is what at least we at Trial Labs and in our experience is the most used in the industry, right? So you have this real problem with real data, lots of data, complex data that you are dealing with. You do a lot of work to preprocess it. You do a lot of feature engineering to decide what works for your model. And then you train some of these normally tree-based methods on this tabular data that you created. And that tends to work really well, and that's what we tend to use in practice with a lot of our clients. But there's been a lot of development in recent years, and even last year, these last few months, on using deep learning for time series forecasting. So this notebook gives a very quick overview on that side of the field. We have almost no time, so I'm going to do a quick intro, then leave you maybe 15 minutes to read through it, and then we can do some questions or go over it quickly. Just skip the exercises. So yeah, the notebook gives a quick intro on why deep learning could be useful for time series forecasting, mentioning some of the things that these tabular models may be lacking, that neural networks are able to represent some patterns or some interactions in the data that these tabular models maybe cannot. Then it gives some examples of models that are like actually used in industry. So DeepAR, NHITS, PatchTST, TFT by Google. There's some models that are kind of all right to use, and that some companies actually go for and deploy in production, and they work really, really well in complex data. So some examples of those. And then it goes into foundational time series models. This is a field that kind of emerged last year. Basically, the idea is we have LLMs that are revolutionizing kind of every field across machine learning. So now they got to time series 2. The idea is to pre-train a huge transformer network in a huge data set of billions of time series and have that pre-trained transformer be able to use it to create predictions on time series that it has never seen before. So that's called zero-shot prediction. So yeah, it's really good because you have this enormous pre-trained model that you can just download and use on your data directly without any retraining. Kind of hot topic at the moment. They don't do really well. There's a little disclaimer here that this is an active area of research, let's say. We do not recommend using this in practice yet, but it's something really interesting that is happening like right now and being developed right now. So we thought it would be fun to mention and fun to use. So we will be training a DeepAR model and using TimesFM, which is one of these foundational models by Google, and according to some independent benchmarks, one of the best ones, best performing ones. So yeah, that's about it. Go through the notebook, and I'll be back in 15. Okay, so that we have some time for questions once we finish this notebook, let's quickly go over it. I already made the introduction to both the models that you need to train and the ones that you don't, these foundation models. Something I forgot to mention is that the fun thing, let's say, about deep learning is that you have these really different kinds of architectures, and for time series, kind of all of them have been applied and used. So you have linear models that can be used. You have recurrent networks, such as DeepAR, that are doing really good. There's even been convolutional networks used for time series. And now with the whole revolution of transformers, those are doing really well too. So it's super flexible, the way in which deep learning has all these different architectures, and time series data can be modified and fed into all of them, and all of them kind of work for time series. So going over the notebook, we start off by training a DeepAR model. As you see, we only train it for, I think, 5 epochs, right? And we are training it on a really small amount of data, and it still takes like 3 minutes or something running on a GPU. So you could see how that would scale to a huge data set. Training one of these big models is really slow, it's really costly. For your use case, that could be all right, that could be the right choice, but then again, it might not. It might be a restriction that just makes it not a possibility to use deep learning at all if you need to train it. And if you look at the results that we got with these 5 epochs of DeepAR, they weren't great. I hope you were able to run it. I'm trying here to get it through. It kind of captured the seasonality in the data, but it was completely overestimating the whole series on the validation set. If you give me just a minute, we should have it here to take a look. So that's where these foundation models come in and kind of may become useful at some point. Again, not a lot of applications that I've heard of at this point, but the interesting thing is you just need to download the model, which is this cell right here. Just define the parameters you want for it. You load it from the checkpoint, which is open source, in this case, luckily. Yep. Yeah. Those are internal parameters of the model. With these foundation models, think of LLMs. You get this like small version, medium version, large version in different sizes and architectures. So this would be, for example, the length of the input series that is consuming, or the length of the internal layers, stuff like that. So you are defining kind of the internal network inside the model. And in this case, you have a fixed set of weights that you need to be able to load into. So this is the only set of weights that they made open source. So if you want to use this set of weights, we need to use the parameters that correspond to them. If you are training it from scratch, you would be able to define whatever parameters you want and train it. But to be able to load this specific checkpoint, you need the correct structure. Right.
And that's according to the documentation is because I forgot what the explanation, but the parameters are coming out of the box.
Yeah.
And if you want to get a better predictions, you should be able to fine-tune those parameters.
Right. So there are some parameters that you can fine-tune. I think there's a note over here. Here, because the model is pre-trained, most of the hyperparameters of the model cannot be configured, parameters that can be configured include context length and window size. Those two correspond to this. Context length is how far in hours the model looks into the past. So that's kind of our concept of lags before. And the other one was window size, which is not here. So yeah, go check the docs for that second one. Sorry. Here. So these are the predictions that we got for DeepAR. Again, one of the most capable and most widely used models. We might have trained it for too little for it to actually do good. But actually, if you kind of see the series, this pattern that it predicted kind of makes sense. You had this upward trend. It captured the seasonality correctly. So this looks like an okay prediction. And then again, for this one, kind of makes sense, the prediction. But for both, it's overestimating quite hard. And once we get the ones from TimesFM, we'll see that in this case, it actually does way better than DeepAR without having had to train it. Maybe it's much slower during inference time. I'm not sure. So lots of things you need to take into account to pick the correct model. But yeah, we just wanted to close the tutorial with this new field, new aspect of the field that is developing right now. That is just fun to see happen. So here are the predictions for TimesFM, more closer to the ground truth. So that's about it for this tutorial. Again, tons of content. Sorry if we cut you off during the exercises a bit. The idea is for the notebooks to be completely self-contained, so you can take them home, and that's material that you can go over or finish the exercises later on if you want to. So yeah, thank you for attending. If you have any more questions, now is the time, or you can come to us once we are done. Thank you.
It's pretty impressive without any training. But like, how could I, like, what do we need to be able to see from this to be able to use it in production? Because I guess like, can't really trust it just yet.
I guess in this case where you don't need training data, you could use your whole training set as a validation set, basically. So you have a huge validation set that you can test this on. Again, if it works for you. And again, this is a huge model. We are deploying it on a GPU. So like actually getting this to production and making it useful for whatever use case you have is a different story. But if that's not a restriction or you decide that's okay for you, this like could be a good choice or even a nice baseline. Like it's really quick to compute these predictions and have this to compare against once you want to do some custom feature engineering or whatever. Yep.
Is it publicly known what time series they use to train it?
I'm not sure on TimesFM specific case. I know there's some models that don't disclose it, some do. I will have to check for TimesFM. There's one called lag-llama. So llama, like in Facebook's Llama 3, etc. It's called lag-llama. That one's open source, and the training data is open source, but it doesn't do really well. It was kind of a controversial topic at the moment. So yeah, like there's some open models with open data sets that they have published. Some other ones don't. I'm not sure this case. What?
Like how if you're using public data?
You don't. So the question was, how do you know it didn't train on your data? So in our case, I know if you are using the M5 dataset, it for sure is using the M5 dataset as part of the training. That's a very famous dataset. So yeah, if you have private data, then you can be sure. If you're using some public dataset, I guess you can't. Okay, I'm not sure what I can say about that. I think it's Kronos. So one of the models I mentioned up here is AWS's Kronos, which is alongside TimesFM and TimeGPT, one of the ones performing the best. I think it's Kronos that literally uses a language model. I think what it do is discretize the input time series into tokens. So transformers work on a fixed vocabulary. So they discretize all the values into a vocabulary, and they use a pre-trained LLM, an actual LLM, to do the prediction. Again, they train over that, but they start off from that, which I found really interesting when reading the paper for Kronos specifically. I'm not sure how you would input this context of this being electricity data into the time series model. Okay, see you around this week.